Good evening, good morning, good afternoon, depending on where you watch this from. My name is Hisham Jared Zige, and from Group 58. Our project is predicting mortality risk after autologous stem cell transplantation using computational machine learning, a comparative and interpretable model analysis. Autologous stem cell transplantation is mostly used in cancer treatment. Most people call it a bone marrow transplant. But in this case, we are looking at male germ cell tumors that are the ones that are being transplanted. This has a high mortality uncertainty, outcomes vary across patients, and clinicians rely on traditional approaches like population statistics, clinical experiences, and genome statistics. They miss individualized risk prediction. This is what my group brings on board. Related works like Sprite use the Center for International Bone Marrow Transplant Research dataset for sickle cell disease patients, achieving a high area under curve values using random forest. Prepared used EBMT registry data and used the XGBoost to predict survival risk in these patients. Machine learning is increasingly used for the outcome prediction, especially survival, relapse, and systematic reviews show common models including random forest regression, SVM, and Bayesian methods, and boosting are the ones that are mostly used. So the problem is that clinicians need patient-level survival insight, and current decisions are based on experience averages. They miss personalized risk prediction. The computational problem, there is a problem to predict binary outcome of survival or death using pre-transplant features. This is a challenge because there is a challenge in achieving this because there would be data leakage, so we try to avoid it and ensure real world validity. Our research objectives included pre-process and prepare transplant clinical data for modeling, develop and compare multiple machine learning models for mortality prediction, to evaluate model performance using the ROC, AUC, and classification metrics to design and deploy a simple interpretable prediction system for clinical use. So our contributions, we developed a machine learning pipeline for pre-processing and modeling transplant data. We built a comparative framework for evaluating multiple models. We identified random forest as the best performing model for mortality prediction. We deployed a simple interpretable prediction tool for real-time clinical use. Our methodology involved cleaning and pre-processing the data, feature engineering, train and test split, model training, model evaluation, and model deployment. The dataset was from the Center for International Bone Marrow Transplant Research, which included 2,395 patient samples, and it was a clinical transplant data. It had 30 original features, but we selected 7 because these 7 were the pre-transplant features that we found relevant to our study. Our target variable was the mortality, which 0 was equal to the alive and 1 was equal to the dead. Class distribution was not so much, it was a bit balanced because 51% were dead and 49% were alive. So these are visualization of graph representing the different features of the dataset. So the dataset is more explained in these graph features. For example, the transplant versus mortality, sub-disease distribution, year of transplant, and then year versus mortality. So on developing the models, we came up with the rankings. As you see in this table, random forest performed better with a test area under curve of 0.64. The mean was 0.65. Logistic regression came second, gradient boosting came third, support vector machine came fourth, and k-nearest neighbors came fifth. And these are also the results explaining how visualizing our result. Although the ROC AUC is not extremely high, this is expected in the clinical prediction tasks. Because mortality depends on many hidden biological and treatment-related factors not fully captured in the dataset. Models achieved approximately 6% accuracy, meaning that 6 out of every 10 patient outcomes were correct. Since the dataset was relatively balanced, accuracy remained a reliable supporting metric. The F1 score showed that models maintain balanced performance between identifying high-risk mortality patients and avoiding excessive false predictions. So we selected the random forest as our best model because although when models were trained in performance, you always default to the one that offers mathematical transparency. A clinician will trust a logistic regression model that outputs clear odds ratios of a random forest black box that outputs just probability, even if forest wins. But so since our task was to take the best model, we took the random forest model because it obtained a 0.01 AUC better than the logistic regression. Yeah, so we selected that, and the scientific justification was it's an ensemble machine learning method. It combines multiple decision trees, reduces overfitting risk, and handles nonlinear relationship and feature interactions. It is robust to noisy clinical variables and moderate class imbalance. This is a demonstration of the product that we developed. It is deployed on Hugging Face. It can seamlessly predict mortality after inputting the age, the Canopy score, the number of transplants, and time diagnosis to transplant. So we went on to do model compression, and random forest was used as our teacher model. The methods used were knowledge distillation, pruning, and quantization. The distill tree had 27 nodes, and as well as the quantized tree, and the pruned random forest had 293 nodes. The accuracy of the distilled tree and the quantized tree was relatively equal, and the pruned tree came last. So our conclusions: random forest achieved the best performance with a test ROC AUC of 0.646. Logistic regression, SMV, and gradient boosting KNN showed similar performance, indicating moderate predictive signal. Knowledge distillation and quantization produced smaller models with only minor performance loss, making deployment more practical. However, we had some limitations. The study used limited number of clinical features, so future work should include genomic markers, tumor biomarkers, treatment response, and longitudinal follow-up data. The study also used only one dataset, so models should be evaluated on external datasets, and the models achieved only moderate performance. So informative features and advanced hybrid or deep learning models should be explored. The next steps is having a richer clinical data, external validation, using advanced models, using explainable feature importance methods, model compression, further knowledge on distillation for lightweight models, and clinical deployment to develop a decision supporting tool in limited in resources, in areas with little resources. So thank you. This is our